Yes, it is visible. Please make it full screen.
So is it full screen?
Yes, it is full screen.
Okay. Good morning, everyone. Uh, Today is the last day of the workshop. So now, my name is Riju Nandi, uh, a PhD scholar under Arnab Ghosh and Krishna Roy sir. So now I'll be discussing about the PCB layout design for DC-DC converter, mainly for the boost converter. And after that, I will testing with Arduino board interface. So start the presentation. Okay. There is my content. Okay. So first is PCB design from KiCad interface. Second, copper plate cleaning. Second, third, printing and pasting on copper plate. Fourth, copper etching. Fifth, drilling and soldering. Sixth is PCB of boost converter. After all the designing, uh, I made the PCB of boost converter. Then Arduino board interface with boost converter. Then conclusion. So, now start the first part PCB design for from KiCad interface. So uh, I have downloaded the KiCad 8.0. Then I have designed the symmetry diagram of push converter in KiCad interface. After complete the PPT, then I will show the KiCad in KiCad that how to do in KiCad little bit. Okay, uh, how to um, how to do footprint, anything, etc. So you can see, say this is the boost converter. Uh, this is the input voltage, then input capacitor is there, then input inductor is there. There is a switch is there. There is a diode is there. There is a output capacitor is there, and the last is load. So after the symmetry diagram, we go for the PCB editor of boost converter. So this is the last part of the PCB design of boost converter. You can see that there is a line with like different depends on your current rating or boost converter. You have to design the PCB design. You have to design the line width. Okay, you can see the figure 3 track width of copper PCB. If for the current 1 ampere, track width if millimeter 10. Okay, for mm 0.25, or for the 2 ampere current, there is a track width 0.76 mm. For the 3 ampere current, track width with 1.27 current, sorry, 1.27 mm. For the 4 ampere current, track width with 2.03. So there is a list is there for the how many current you want. Depends on the current, you have to design the line width. Okay. Suppose for my boost converter, I have designed for the 8 ampere current. So my track width is 5.59. Have you seen that? You can see that my track width is like width is greater than this side. Also, this line width is 5.59. Okay. Uh, uh, okay. After this is the first part of the designing. Okay. From starting the hardware process, we have to design in KiCad software. Uh, Boost converter. Okay. After completing the PPT, I will show the design in KiCad software. Okay. So now going the copper plate cleaning. First, we have to cut the copper plate. Depends on your size. Okay. There is a we will be making the power supply. You can see how to make the power supply. There will make plus minus 15 volt power supply. A figure for the before copper plate cleaning. This is the after cutting the copper plate. Okay, this is the copper plate cleaning. After before the copper plate cleaning. After this is the after copper plate cleaning. So I have done the copper plate cleaning with using the shampoo, soap, anything. You have to clean the copper plate. Okay. So why we do the copper plate cleaning? Okay. First is contaminant like oil, grease, dust, or dirt can cause poor electrical connection, short circuit, or open circuit after the PCB is fabricated. So the cleaning like copper plate minimize these risks and helps ensure reliable operation. During the PCB manufacture process, copper is selectively removed by etching. A clean surface allows the etching process to proceed uniformly. If any dust is there, for the etching part there is a problem. So avoiding unwanted material left behind that could cause signal interference or faulty connection. If copper plate is dirty or oxidized, it becomes harder to solder component onto the PCB. A clean surface ensures that the solder can form strong, reliable joints. Okay. So second part is you can see this printing and pasting on copper plate. That first figure number 6, you can see that PC print and copper plate separate. So you can say there is a white paper is there. Okay. After designing the PCB in KiCad, we have to print in glossy paper. Glossy paper. You have to print in glossy paper. Then you can see the figure 7 PCB print paper on copper plate. So, PCB that print paper you have to uh, you have to I'm
And now,
audible. Sir,
now
am I
you're
audible?
audible.
Sir?
Yes, yes.
So
Share it
okay,
in.
so okay. So is it visible?
Yes, yes.
Okay. Oh, so now figure 6, you can see the PC print and cover plate are separated. Okay, there is a glossy paper. You have to print in glossy paper the PCB designing, and the copper plate are separate. Then you go for printing process. So you have to do that that glossy paper put on the uh, PC copper plate. So then you can see the figure during pasting by iron. Okay, that time I have done the pasting means with ironing part I have to paste the and that that the bush power supply circuit diagram on the copper plate. Okay, why we have done this? So first for the PCB layout and the printed on on special transfer paper or glossy paper. I have told that we have used the glossy paper. So that glossy paper using a laser printer we have to use the laser printer. Other printer, if you use the other printer, that won't be affect in the copper plate. So you have to use the laser printer. Then needs to be transferred accurately to the copper plate. So you have to that printed part, that line part, PCB line part, you have to transfer accurately the copper plate. If you some line has been missing now, the line has been missing, that will be problem your circuit. Okay, that won't be completed the your circuit, so your circuit won't run. So the ironing process uses heat and melt the toner. Uh, I have told that I have using I have I have used iron for the pasting. So the ironing process uses heat and melt the toner, causing it to adhere to the copper surface effectively and transferring the design. Uh, after the heating, from iron, that printed part transferring the design to the copper plate on the copper plate. Second part is applying heat and pressure during ironing that the toner bonds well with the copper surface. I have told about it, and creating a clear, sharp transfer of the circuit diagram. Without proper bonding, the design may be incomplete and or inaccurate, leading to error in the final PCB. I have told already that if your design has not completed, means maybe incompleted or inaccurate, that time you got a error. Okay. Second, so the ironing process is a simple, low-cost method for a small case PCB manufacturer to create PCB prototype without the need for expensive equipment like photolithography machines. It's an accessible method for transferring complex PCB design onto copper quickly. Last point is the well executed ironing process ensure that the transfer toner pattern remains intact during the etching process. Poor adhesion or incomplete transfer could result in the attacking areas it shouldn't. Attacking area it shouldn't, leading to broken or shorted traces. Now I'm discussing about copper etching. You can see that figure 9 is the copper etching. So using ferric chloride for the copper etching, you can see that four power supply plate is there. Okay. On the copper plate, there is a ferric chloride is there. So we have used the ferric chloride for the copper etching part. Uh, okay, the ferric chloride is switchable for the copper etching because it is low cost also, or it will affect nicely in the for the copper etching. So the figure 10, you can see this is during copper etching. Okay, after putting the ferric chloride, after 5 to 10 minutes, you have to put the water, some water, then shaking the that box with water during copper etching. After this figure 11, you can see after copper etching, you can see the result. Uh, we got the power supply. PCB designing. Okay, there's all the copper has been removed, and only designing part is there. Only designing part is there. You can see it is nicely printed in the on the copper plate. So why we have done this? So ferric chloride, we use the ferric chloride. So ferric chloride is the relatively easy to handle and doesn't require extremely high temperature or special equipment. It's commonly available and can be used at room temperature, making it ideal for industrial and DIY application. So ferric chloride is relatively inexpensive. uh, I already told it is low cost, widely available, and can be used multiple times by regenerating the etching solution. Then, unlike some other etching chemical such as nitric acid, ferric chloride is less volatile and doesn't produce dangerous humus during the etching process, making it safer to use under control condition. Then, copper etching removes the unwanted copper from the surface of the board, leaving only the desired circuit pattern behind. You can see uh, all the copper has been removed except that copper plate line, designing line. There is a copper is there. Behind that black line is copper line is there. So except that line, all copper has been removed. So leaving only the desired circuit pattern behind. So this pattern acts as the wiring system on the PCB, guiding electrical signal between components. So copper etching allows for the creation of fine tail circuit paths, enabling the design of compact and high density circuit. Etching enables the creation of custom PCB layout tailored to specified electrical design and requirements. Designer can create highly complex circuit with multiple layers by stacking copper traces separated by insulating layers. Thanks. Uh, so once the design is finalized, uh, the etching process can be automated and scale for mass production. If you go any company for mass production, uh, the etching process can be automated. Okay, and the scale for the mass production, allowing the manufacture of large quantity of PCB at low cost. The width and thickness and the path of the copper trace can be controlled during the etching process to reduce resistance, inductance, and capacitance, which can impact signal integrity and power delivery. So the next part is drilling and soldering. So we haven't captured the drilling and soldering part. Means uh, drilling and soldering is the easy part. You have to drill. There is a you can see figure 11. There is a hole is there. Okay, you have to drill that whole part. Okay, after drilling, you go for soldering. Okay, you go for soldering. So drilling and soldering. Uh, is drilling is done to create holes in the PCB. Drilling is done to create holes in the PCB for the placement of electronic component and to establish electrical connection between different layers in the board. Uh, Traditional through whole component like resistor, capacitor, and any IC integrated circuit. Suppose for driver TLP250 circuit is there. So any supply we have used for 7 or on 5 like that for the plus minus 15 voltage supply. Have leads that needs to be inserted through the board. Drilling creates holes where this component leads can be inserted before soldering. So I have already told that you have to drill before the soldering. After the drilling part, you have to put the all the resistor, capacitor, and IC, and then you have to do soldering. So before soldering them to the copper parts, securing them to the PCB and electrically connecting them to the circuit. So drilled holes are also used for mounting screws or standoffs that physically secure the PCB inside a casing or chassis. So uh, now, now I'll be discussing the soldering part. So soldering is the process of attaching component to the PCB by melting solder uh, to from electrical and mechanical connection between the component leads and the copper parts. Uh, you have to do the soldering after the drilling part. So after inserting through hole component into drilled holes or placing surface mount components onto copper parts, soldering ensures the permanent electrical connection between the component terminal and the copper traces. The molten solder flows into the hole and around the component lid and forming a conductive bridge between the component and the PCB. So, our solder provides mechanical stability to the component and preventing them from moving or becoming loose when the device is handled or vibrated. So, solder provides this mechanical stability. I have already told that if uh, if uh, you won't do the proper soldering, that is uh, for moving that component will becoming loose, the device is handled or vibrated. Okay, the proper soldering ensures a strong and low resistance connection, which is crucial for the performance and reliability for the circuit. Poor solder joints can cause intermittent connection or even failure of the device. If you have done the poor soldering, it is cause intermittent connection or failure of the device. Uh, Okay, so uh, so I have discussed about the all the PCB design part of the power supply. So uh, like that, we have done all the boost converter, back converter, any converter, also the driver circuit, supply circuit, any circuit we have designed in our lab. So uh, after the PCB design, I have designed the you can see I have designed the boost converter. So you can see this is the boost converter. The upper part is the boost converter. Okay, and then the lower part there is a DC supply is there, and driver circuit is there. Okay. That 15 voltage DC supply is there. We have made I have shown that we have made that power supply. That power supply you have designed. Okay. In PPT also I am shown. Also I have designed the boost converter and the driver circuit. You can see there is a boost converter. We have used the diode. This is the high frequency diode because we have used for 20 kilohertz frequency. That's why I have used the high frequency diode, and this is the MOSFET. So I have used MOSFET for the high frequency. Okay. Also power rating also. So that the backside inductor is there. Backside inductor is there. So our inductor value is 250 microhenry. So depends our specification. We have to design the inductor. So we have designed our own hand the inductor. So these you can see there is a output capacitor. This is the input capacitor. So we have bought the capacitor. We have bought the capacitor. Then connecting to the PCB board. Also, you can see there is a driver circuit is there. So this driver circuit is TLP 250 driver circuit we have used. TLP 250 is a driver circuit you used. Okay. This is the 15-volt DC supply. This is the 15-volt DC supply we have used for the mm, getting for the input for the driver circuit. After the driver circuit, uh, after the driver circuit, it will make the duty ratio, then pulses uh, uh, go to the MOSFET. For the MOSFET, get to source MOSFET, then boost converter will run. Boost converter will run. Oh, you will see that how to do the uh, Arduino interface for the gate pulse. We have used Arduino for the gate pulse. Suppose duty
मेरा तो कोई
ratio.
रोल ही नहीं है उसमें।
तो यही कह रहा हूँ वो अब सिर्फ अपने मुद्दे की बात कर रहा है बस। अगर इतनी परेशानी हो रही डायरेक्टर पे, वो क्यों नहीं गया, उसका लड़का क्यों नहीं गया, कुछ नहीं कह रहा। इस बात को मैं मान सकता हूँ कि वो होगा तेज, मगर ये भी जानबूझ के कहीं उसको कुछ कह नहीं पा।
Okay. That PCB design part, the PCB design part has been completed. PCB design for picker interference, copper plate cleaning, printer and pasting of copper plate, copper etching, drilling, soldering, and PCB of boost converter has been completed. Now I will go for Arduino board interference with boost converter. Okay. Uh, okay. So wait. Okay. 1 minute. Okay. So now I have told that after that presentation of Bush converter PCB design, I'll be discussing about KiCad software. So you can see that is the KiCad software interface. Sir, am I audible, sir?
Yes, you are audible. Carry on.
Okay, okay. Uh-huh. You can see this is our KiCad 8.0 software. You can see this is a KiCad 8.0. In this KiCad 8.0, we have designed the boost circuit. So you can see, uh, you can see we have designed the boost converter. So there is a V1, V2 for the input voltage terminal and the input capacitor for the input inductor, okay, so means inductor, and uh, for the switches and the diode, for the switch and the diode I have been used that 3 pin point, and this is the output capacitor. This two-piece terminal, 2-point terminal we have used. Also, this is the for load. We have to make sure that for the designing the PCB, we have to do correctly footprint. Suppose you go to the if you go to the tools, assign footprints. If you go to the assign footprints, let's see. There's some. It takes some time for the loading footprints. Hmm. You can see for the C1, C2, I have used connector banana jacks 1 pin. For the C2 also banana jacks 1 pin, and for the CI1 and CI2 the connector banana jeans. Okay, for like that we have used. Okay, for V1 V2 for R1 R2 banana jacks 1 pin, for the J1 connector terminal block terminal 1 5 which is 5.08 with depends on our equipment material. We have to focus on your footprint, because if your footprint is incorrect, that time you won't be able to soldering. We are able to solder your equipment, means any capacitor, resistance, IC, anything. You have to design correctly your also footprint. Okay. So after designing the boost converter, uh, this is a symmetric diagram of boost converter. So if you go to the after symmetric diagram, if you go to the boost editor, you can see hmm, you can see I have done that boost converter nicely. So we have to connect properly. So your circuit must be not complex, must be not complex. It have to easier. See the you have to join the circuit. Your circuit won't be complex. So I have already told that my line width is 5.59. You can see my track width is 5.59 for the 8 ampere current. Depends on your current. Uh, Depends on current rating. You have to do. You have done your uh, copper path, uh, copper width. Okay. So you will decide what you want, what what is your current rating. Okay. Depends on your current rating. You will uh, you will make the your PCB design. So if you go to the view, if you go to the 3D view, you can see this is our 3D view. Okay. This is our 3D view of the PCB design. If you go to after after making the PCB design, you can see our PCB design like that. Okay, this is the input voltage, input capacitors, the inductor, this is the resistance, this is the output capacitor, this is a switch and diode also. This is switch and diode. Okay, if you go to like that, there is a you have to soldering like that. Okay, this is the part. Okay. So this is the our 3D view. So PCB design has been completed. Now I'll be going. I'll be discussing about the Arduino interface. In my desktop now I'm doing laptop, but in my desktop that Arduino interface is there. So I'll go to desktop. Then I'll show the how to do the Arduino interface. Uh, uh, Arduino interface for the boost converter. Okay. Uh, uh, because because uh, because for the gate pulse means D2 ratio, we have to sorry. Uh, so sorry. So for the gate pulse of the boost converter, we have to do the Arduino interface. Okay. So let's see how to do the Arduino interface. Okay. So what? 1 minute.
Hello.
Hello.
Sir, nothing is audible. Whether it is going or
It was going on, no?
No, sir.
but we are not able to see even slide also.
Maybe you have joined recently. The program is going on, so it's changing the system. Now maybe that's why some transitions it is blank. Please be online. You see.
I'm in online only, no?
Riju,
Sir, slides are not visible.
Wait, wait 1 minute. Wait 1 minute. Wait 1 minute. Sorry for interrupting.
Okay.
आपका लैपटॉप है?
चावल भिगा दिए आपने चावल भिगा दिए आपने
हाँ. So now I'm discussing about the or So uh, so you can see Mhm. Uh, you can see that this is the Arduino interface of the so this is the our Arduino interference. So for the MATLAB, we have used the MATLAB. So firstly, you have to download the uh, uh, first you have to download the Arduino Simulink support package of for Arduino hardware. So you have to download the all the things. Then you have to do it. So if you won't download that support package, you won't be able to do the uh, won't be able to do the uh, Arduino interface. So there uh, you can see I have been used the pulse generator. So there I have used the pulse generator. There's a amplitude is 1 and time is 1 by 20 hertz. Means 1 by f means 1 by 20 kilohertz. Uh, for the 20 kilohertz I have been used. Okay. Your for the DT ratio or anything your switching frequency must be higher like 20 kilohertz, 30 kilohertz, 25 kilohertz, 50 kilohertz, like that. If your switching frequency is lower, like suppose 1000, 2000, it won't be affect it will be affect your for switching for the D2 ratio. Also for your this, MOSFET also. If your frequency is low, that time for that time I think your switch also shorted and your for and because of shortage gate to source for your switch will be fail. Okay, there is a pulse width I kept at 50%, means 50% I kept in 50%. Okay, I have used that the Arduino PWM Arduino. So you have to go the library browser, then go to that Simulink support package, then go to the common. If you go to the common, there is a many output is there. Uh, uh, you can use digital output. Okay, you can use also that this PWM. For the pulses duty ratio, it is switchable. For that PWM is switchable uh, uh, for the pulses. Okay, so I have used that PWM. So if you go to that PWM, you have to fix your number or which pin number you want to get the output. For the I have used Arduino 2560. For the pin number 3, we have used for the um, output. So go to the frequency, you have to specify your frequency. So I have used for 20 kilohertz. So you have to put the 20 kilohertz, then apply. Then you can see that achievable also 20 kilohertz, desired also 20 kilohertz. It will change automatically. So go to the OK. Okay. Go to the OK like that. So we have designed this. So this is the design of Arduino. So now I will be showing how to uh, build in Arduino. How to build in Arduino uh, for in this MATLAB simulation. MATLAB Simulink. So I already told that I have designed all the things. Okay, this is the PW pulse generator, and this is the PWM. So we have to build in Arduino this simulation. So we have already connected. Now I have already connected the Arduino. Okay, Arduino. I have used Arduino 2560 at Mega two Arduino Mega 2560. Okay, now you have to go the hardware portion. Go to the hardware portion. Uh, then go to the hardware setting. If you go the hardware setting, you have to choose. Suppose you choose. Suppose you are using Arduino Micro or Arduino UNO. Okay, depends on your Arduino. You have to choose that the Arduino file. Okay, now I have used Arduino Mega 2560. That's why I have choose to Arduino Mega 2560. Then go to the hardware resource button. Go to the host right. So you can see there is a automatically it will default it will showing suppose 11 500 200. Okay, you won't change anything. Okay. Uh, so after that, go to the OK. Then go to you can see there's a monitor and tune part is there. You have to stop time, do the infinity INS, then go to the monitor and tuning. If you click the monitor tuning, then it will show in Arduino. Some lighting part is there in Arduino. It will showing that monitor tuning is going on in the Arduino at Mega. Now it's lighting is going on in Arduino. Some lighting is going on. Okay. So after sometimes after sentence we'll build and deploy the MATLAB simulation in the Arduino files. Okay. After the putting the after build the Arduino MATLAB simulation, we'll go for the testing. Is testing in the boost converter. So that camera part I'll do. Okay. In my laboratory I'll do that. This. So you can see that uh, uh, it's already tuning part. So go to the stop button. Then go to the build, deploy, and start. If you click that part, also after clicking that Arduino, some lighting is there. Then it have shown that it has shown that they already built the simulation. Simulation means G2 ratio already built. So take 1 minute. So already I have built. You can show that one model build. Okay, build duration has been completed. So now I'll go to the lab. So then I'll be testing that D2 ratio in the push converter. Then we'll put the input voltage, then we'll get the output voltage. You can see. Okay, wait for 2 minutes.
Hello, sir. Hello.
Hello. Good morning, sir.
Sir, good morning. Is my voice audible?
Good morning, sir.
Sir, no one presentation here now.
Riju was presenting. Yes, Riju.
Okay.
Uh, so now am I audible? Oh, sir.
Yes, you are audible. Please carry on.
Okay. Now I'm going to testing. I'm going to testing the boost converter with the Arduino UNO because some issue Arduino my ATmega now not working. That's why now using also Arduino UNO. There's a you can saw that I have built this a 30% D2 ratio has been uh, implemented. Okay, so and 20 kilohertz frequency. So you can see, okay, that D2 ratio I um, put in the gate pulse. Okay, so you can see this is the our power supply. So this is the boost converter, and 0.3 is the D2 ratio. Depends on our D2 ratio. You know that for the D2 for the boost converter v0 equals to v in by 1 minus d. Okay, so if you increasing the voltage, now I'm increasing the voltage. So now I'm increasing the voltage. You can see the input voltage is 10 voltage. Okay, input set in 10 voltage, and duration is 0.3. Okay, duration is 0.3, and if you measure the output voltage, what is the output voltage? Okay. See what is the output voltage? You can see the output voltage is near about 14 voltage. Okay, so if you calculate what will be the result? So if you 10 by 1 minus 3, suppose in calculate part 14.28 voltage have to come, but for the hardware some drop has been happened. That's why I got the value of output voltage is like that 13.8 voltage. You can see 13, suppose a point, suppose 0.5 to 6 voltage has been dropped. Okay, this is a boost converter. I already told in the PPT. This is the boost converter by the PCB designing. Wait 1 minute. You can see that this is the boost converter we have designed. Already. This is our power supply. This is our this is our driver circuit. This is our supply circuit. This is our boost converter. Okay. I already told about this. How to do that? How to do the PCB design, and how to do soldering and drilling part. Okay. After the drilling part, we made also that inductor part also. Okay. Then after completed the boost converter, now I have been tested already. So I have successfully tested the boost converter. You can see if you go for also 20 voltage, 30 voltage. Okay, maximum current rating it is 8 ampere. Maximum current for the boost converter is 8 ampere. It will it is after 10 ampere or after 11 ampere, it won't it will be affect. Yeah, that time I think failure will happen. That's why up to 8 to 9 ampere I have designed the boost converter. So I have been successful tested. You can see. So now laboratory session has been completed. Now I'm go for conclusion. So wait for 1 minute. Sir, am I audible, sir? Hello, sir.
Yes, you are audible.
Okay, sir.
Carry on. Carry on.
So I have completed all the things. Firstly, PCB design of PK interface, copper plate cleaning, then printing and pasting of copper plate, then copper etching, then drilling and soldering, then PCB boost converter. Then I have tested all the things like Arduino board interface, how to test the Arduino board interface with the boost converter, how to get the result. Okay, then come to our last part in conclusion. So the PCB design and copper etching of the boost converter in PTAT successfully done. You can you have already shown that I have I have done all the PCB design copper etching of the boost converter, and pulse generation through Arduino using MATLAB simulation is done and verified using DSO. Uh, uh, we already shown that in DSO, 0.3 duty ratio has come. Okay, 0.3 duty ratio and 20 kilohertz is the frequency. So the pulse generation through Arduino using MATLAB is done, and the last part, the design boost converter is tested and verified. So you can you have already shown that uh, I have given supply in 10 voltage DC supply and got the output near about 14 voltage. So for 0.3 duty ratio. So for the practical also we have got the good result. Okay, so that's all for my side. Thank you. So any question? So any question? Any inquiry? Any inquiry, sir?
If you have any query, please let us know. Any queries?
Any queries for anyone?
Okay, there is no query. Okay, so Riju, I hope your session over, am I right?
Yes, sir. Yes, sir. First,
Okay, so